Space, Humanity's Infinite Frontier. Introduction. The allure of the cosmos. Since the dawn of civilization, humans have gazed at the night sky with wonder. The stars, planets, and celestial events have inspired myths, guided explorers, and sparked scientific revolutions. Space is not merely a backdrop to our existence. It is the vast, dynamic stage upon which the drama of the universe unfolds. As our understanding deepens, so does our desire to explore, comprehend, and perhaps one day inhabit the cosmos. Defining space. Beyond Earth's atmosphere, space begins where Earth's atmosphere ends, typically defined by the Kármán line, located about 100 kilometers, 62 miles, above sea level. Beyond this boundary lies a realm of near-perfect vacuum, where gravity still exerts influence, but air pressure and molecular density drop dramatically. Key properties. Vacuum conditions. Space contains very few particles per cubic meter, making it inhospitable to life without protection. Microgravity. Objects in orbit experience continuous free fall, creating a sensation of weightlessness. Cosmic radiation. High-energy particles from the sun and distant galaxies permeate space, posing risks to biological organisms. Temperature extremes. Without atmospheric insulation, temperatures can swing from hundreds of degrees Celsius in sunlight to near absolute zero in shadow. The architecture of the universe. The universe is structured in layers of complexity, from subatomic particles to galactic superclusters, celestial bodies, stars, nuclear furnaces that fuse hydrogen into helium, emitting light and heat. Our Sun is a G-type main-sequence star. Planets, bodies orbiting stars ranging from rocky, like Earth and Mars, to gaseous, like Jupiter and Saturn. Moons, natural satellites orbiting planets, some with subsurface oceans, e.g. Europa, Enceladus. Asteroids, and comets. Remnants from the solar system's formation, often rich in metals or ice. Larger structures, solar systems, a star and its orbiting bodies. Galaxies, massive collections of stars, gas, and dust bound by gravity. The Milky Way is our home galaxy. Galaxy clusters and superclusters. Groups of galaxies forming the largest known structures in the universe. Nebulae. Clouds of gas and dust where stars are born or die. Black holes, regions of space with gravitational fields so intense that not even light can escape. Cosmic phenomena, dark matter, invisible mass that exerts gravitational effects, comprising 27% of the universe. Dark energy, a mysterious force driving the accelerated expansion of the universe. Cosmic microwave background, radiation left over from the Big Bang, offering clues to the universe's origin. The history of space exploration. Humanity's journey into space is one of the most remarkable chapters in technological history. Early milestones. Sputnik 1, 1957. The first artificial satellite, launched by the Soviet Union. Yuri Gagarin, 1961. The first human in space, aboard Vostok 1 Apollo 11, 1969. Neil Armstrong and Buzz Aldrin become the first humans to walk on the moon. The space race. The Cold War rivalry between the U.S. and USSR accelerated space exploration, leading to rapid advancements in rocketry, satellite technology, and human spaceflight. International collaboration. International Space Station, ISS, a joint project involving NASA, Roscosmos, ESA, JAXA, and others, serving as a laboratory, and living space in low Earth orbit. Global missions. Countries like China, India, and the UAE have launched ambitious missions to the Moon, Mars, and beyond. Scientific disciplines and space research. Space science is a multidisciplinary field encompassing physics, chemistry, biology, and engineering. A astronomy and astrophysics study of celestial objects, their movements and physical properties. Investigates phenomena like supernovae, quasars, and gravitational waves. B. Cosmology explores the origin, structure, and fate of the universe. Central theories include the Big Bang, cosmic inflation, and multiverse hypotheses. C. Planetary science examines the geology, atmospheres, and potential habitability of planets and moons. Mars, Titan, and Europa are key targets for future exploration. D. Astrobiology seeks to understand the conditions necessary for life. Investigates extremophiles on Earth and biosignatures on other worlds. E. Space medicine studies the effects of microgravity, radiation, and isolation on human health. Develops countermeasures for long-duration missions. Technological innovations. Space exploration has driven technological breakthroughs with wide-ranging applications. A. Rockets and propulsion. Chemical rockets remain the primary method of launch. Emerging technologies include ion propulsion, solar sails, and nuclear thermal engines. B. Satellites used for communication, navigation, GPS, weather forecasting, and Earth observation. Thousands of satellites orbit Earth, forming constellations like Starlink.c. Telescopes, ground-based and space-based observatories, e.g. Hubble, James Webb, provide insights into distant galaxies and exoplanets. D. Robotics rovers like Curiosity and Perseverance explore Mars autonomously. Robotic arms and drones assist astronauts on the ISS. 7th. Challenges of space exploration. Despite its allure, space is a hostile and unforgiving environment. Radiation exposure can damage DNA and increase cancer risk. Psychological stress, isolation, and confinement affect mental health. Resource scarcity. Life support systems must recycle air, water, and waste. Communication delays. Signals to Mars can take up to 22 minutes one way. Cost. Launching missions requires billions of dollars and years of planning. Aid. The future of space, vision and possibility. The coming decades may redefine humanity's relationship with space. A. Mars colonization. NASA and SpaceX plan crewed missions to Mars by the 2030s. Challenges include radiation shielding, sustainable habitats, and food production. B. Lunar bases. The Artemis program aims to establish a permanent presence on the Moon. Could serve as a launch pad for deeper space missions. C. Space tourism companies like Blue Origin and Virgin Galactic offer suborbital flights. Long-term vision includes orbital hotels and lunar vacations. D. Asteroid mining potential to extract rare metals and water from near-Earth objects. Could support in-space manufacturing and fuel production. E. Interstellar. Exploration concepts like Breakthrough Starshot propose sending probes to Alpha Centauri, requires breakthroughs in propulsion and miniaturization. X. Philosophical and cultural reflections. Space exploration raises profound questions about existence, identity, and destiny. Are we alone? The search for extraterrestrial life challenges our understanding of biology and consciousness. The overview effect. Astronauts often describe a transformative sense of unity and fragility when viewing Earth from space. Cosmic perspective. Recognizing our place in the universe fosters humility and curiosity. Cultural impact. Space inspires art, literature, music, and film. From 2001, A Space Odyssey to Interstellar Dax. Conclusion. Humanity's cosmic journey space is not just a destination. It is a mirror reflecting our deepest aspirations and fears. As we venture further into the cosmos, we are not merely exploring stars and planets. We are exploring the boundaries of possibility itself. The universe beckons with infinite questions, and each mission, each discovery, brings us closer to understanding the grand tapestry of existence.